A stationary wave is set up on a stretched string of length L and diameter d. Another stationary wave is also set up on a second string made from the same material and with the same tension as the first. What length and diameter are required for the second string so that both strings have the same first harmonic frequency? Okay, so the equation that we want to be using here is frequency for the first harmonic is equal to 1 over 2 times the length of the string divided by the square root of tension divided by the mass per unit length. You might be given that equation in your formula booklet. You might instead be given this one, V is equal to root T over mu. So if you're given the second equation, this one over here, then you want to be able to go from this equation to this one. So we do so by considering V is equal to F lambda, and wavelength being equal to 2 times the length of the string. That's for the first harmonic. If we have a wave on a string, so this is a sketch of the first harmonic, let's say the length is equal to L. This here represents half of a wavelength. A full wavelength will be this plus this. This would represent one full wavelength. That's the wave shape. So then double this length to get one full wavelength. That would be 2L. That would be the wavelength for a wave on a string for the first harmonic. So then to get this equation here with these three equations, you replace the lambda with 2L. So put this 2L into there and then replace the V with that F times 2L. And then just rearrange and you'll end up with this equation here. Okay, so in our question, we're told that length and diameter can be changing. We have different options. We're trying to see which pair of length and diameter will have the same first harmonic frequency. We see length in our equation here, but we don't see diameter. Diameter is not in this equation, at least not directly. So we need to find a way to get diameter in there, and we can do so by considering mu, which is the mass per unit length. Mass is equal to density times volume, and the volume of a wire is equal to the cross-sectional area times length. So volume is equal to cross-sectional area times length. I'll just draw a very quick sketch so you can see that. Here's our wire, this is our cross-sectional area, and this is the length, times the two things to get the volume. The lengths then cancel, and the mass per unit length, mu, can then be rewritten as cross-sectional area times density. Okay, so area is pi r squared, or pi d squared over 4. That's how we get diameter into there. To go from here to here, I just replace the radius with d over 2. And so in the question it says that both strings are made from the same material. If they're made from the same material, that means that the density will be the same. So if the density is the same, looking at this equation that we have here, we can see that the mass per unit length mu is proportional to the cross-sectional area. And looking at this equation here, we see that the cross-sectional area is proportional to diameter squared. Put those two things together, and we get mu is proportional to d squared. If mu is proportional to A is proportional to d squared, then mu is proportional to d squared. Okay, so now let's go back to our equation and think about how proportionalities work with that. So this is what we have. What's changing, what's constant? Well, the length can change. The mass per unit length can also change. The tension is constant though. It says in the question that the two strings have the same tension. So then frequency would be proportional to 1 over length times the square root of mu. So those are the things that are changing or can change. Frequency is proportional to 1 over the length times root mu. So we know that mu is equal to or proportional to d squared. If we replace the mu that we have here with d squared, the square root and the square cancel and we get frequency is proportional to 1 over LD. So these two things are multiplied together. In the question it says that both strings have the same first harmonic frequency. So in order to have the same first harmonic frequency, because L and D are multiplied together, the factors by which they change when multiplied together should cancel out. So for instance, if L were to double, then D should half. If L were to get multiplied by a third, then d should get multiplied by 3. If we look at our options, what achieves that is option C. For option C, the length halves and the diameter doubles, so those two factors will cancel out in this denominator, and overall the frequency will then not change.